All right, welcome back. In this explainer, we're diving into Distributed Data 34, focusing on consistency models. We're going to tackle one of the most absolutely fascinating and, frankly, most frustrating tensions in back-end engineering. You see, when you're writing code on a single machine, life is pretty predictable, right? You assign a value to a variable, you read it back a millisecond later, and boom, it's exactly what you expect. But what happens when we take that data and scatter it across a massively distributed network of machines? Well, the predictable nature of your code collides head-on with the chaotic reality of distributed systems. So today, we are breaking down consistency models and a really cool concept known as the single copy illusion.
Okay, let's dive into this. Here is a clear roadmap for our whiteboard session today. We'll start with the replication problem, move on to when stale reads fail, explore the single copy illusion, discuss the cost of coordination, and finally, wrap up with choosing your guarantees.
Starting with Section 1, the replication problem. Why do we even distribute data in the first place? Before we can even talk about consistency, we have to ask ourselves, what actually happens when data lives everywhere? We're leaving the safe, cozy confines of a single machine's memory where variables just behave themselves. Instead, we're stepping into a world where data is copied and spread across servers, racks, and literally entire geographic continents.
Now, we do this to ourselves for three very good reasons. First up is fault tolerance. If a machine catches fire, we obviously don't want to lose our data. Another node needs to instantly step in. Second, lower latency. We replicate data so it physically sits closer to our users all around the globe. And third, scalability. A single machine simply cannot handle the massive read and write volumes of a modern application. But, here is the catch. The exact moment you replicate data, you introduce the chaotic reality of network delays. Information takes time to travel, meaning your copies will inevitably, for sure, fall out of sync.
To tame all that chaos, we use consistency models. Think of these as the magic rules that force a distributed, replicated system to actually behave predictably for the end user. They define exactly what a user is allowed to observe when data is being copied, delayed, or updated concurrently across the network.
Which brings us to Section 2, when stale reads fail, or the eventual chaos. Now, what's really interesting about this slide is how it plays out in real life. Imagine Alice and Bob are watching the World Cup final, sitting in the exact same room. The game ends. Alice refreshes her phone, her request hits a fully up-to-date database leader, and she shouts, "Germany won." Bob hears this, immediately hits refresh on his own phone, but his request gets routed to a database follower that's just a little bit lagging behind. His screen says the game is still ongoing. Because Bob initiated his query after he heard Alice's results, he naturally expected his phone to be at least as up-to-date as hers. This right here is the classic stale read. Now sure, a delayed sports score is just confusing, but let's ground this concept in some high-stakes scenarios where eventual consistency isn't just annoying, it's completely system-breaking. What if that wasn't a sports score, but an account balance? A stale read could let someone withdraw money twice, dropping the balance below zero. What if two users try to register the exact same unique username at the exact same millisecond? Or what if a lagging node thinks the primary database is dead, elects itself as the new leader, and causes a massive split-brain scenario where two different servers both think they're in charge? Or an e-commerce store overselling its limited inventory? These aren't just glitches, they are absolutely critical failures. Let's move on to Section 3, the single copy illusion. And the magic trick that solves this, linearizability. Let's quickly contrast these two worlds. Eventual consistency acknowledges the chaotic reality. Your replicas will converge eventually, but in the meantime, your reads might be stale. Linearizability, on the other hand, provides a very strict expectation. It projects the illusion that there is only one instantaneous copy of the data in the entire system, and all operations act on it atomically. And this brilliantly illustrates how the illusion works in practice. In a linearizable system, once a new value is read by anyone, all subsequent reads absolutely must also return that new value. Look at Client A. Once Client A successfully reads the value 1, a timing dependency is created. Client B, who queries the system after A, is absolutely forbidden from reading the old value 0, even if the background write operation is still technically propagating across the network. The system is forced to enforce this strict order. As the source material states so well, linearizability is ultimately a recency guarantee. It's a rock-solid promise that any read will return the most recent, up-to-date value. It seriously doesn't matter if you have 50 replicas spread across 3 different continents. The system must project the illusion that there is only one single register, updated in a perfectly straight linear timeline. Section 4, the cost of coordination. Let's pull back the curtain and look at the catch. To enforce this linearizability, your nodes have to constantly talk to each other to agree on the state of the data. That requires heavy coordination. And as we know, coordination takes time, which means your latency penalty is high. But the most severe penalty happens during a network fault. If a node gets disconnected, a linearizable system actually has to halt operations entirely to avoid serving stale data. In contrast, an eventually consistent system, it just shrugs, serves whatever data it has on hand, and continues working with nice, low latency. This trade-off is formalized by the famous CAP theorem. But please, don't think of CAP as dusty academic theory. It is the direct, unavoidable physical consequence of demanding linearizability during a network partition. If the network cables between your data centers literally get cut, you simply cannot have both. You must choose. Do you maintain that single copy illusion and make your system completely unavailable? Or do you stay online, fully knowing your users are going to see non-linearizable, stale data?
Now, you might be sitting there thinking, hey, I use a Dynamo-style database like Cassandra with strict quorum reads and writes. I'm totally safe, right? Actually, scratch that. You're not. Let's move to and see how this builds, because even with strict quorums where you write to a majority of nodes and read from a majority of nodes, you can still violate linearization ability.
Let's break down the exact steps of this quorum race condition. Step 1. A write request comes in, but it overlaps in time with 2 parallel read requests. Step 2. Because network delays are completely unpredictable, the write reaches some replicas faster than others. Step 3. Reader A connects to a replica that got the fast write, so they see the new value. But reader B connects to the slower replicas, and they receive the old value. The illusion is totally broken. Varying network delays have successfully tricked your strict quorum into serving a stale read. No way around it. Section 5. Choosing your guarantees. Let's talk about real-world architectural choices. So the crucial point is this. There is no silver bullet here. Consistency models define the promises your architecture makes to your users. And in distributed systems, stronger promises always require heavier coordination. As an engineer, you can't just default to the strongest guarantee because it sounds nice. You have to actively choose the consistency model that perfectly matches your application's strict correctness needs. You should really only accept the heavy performance and availability hit, what we like to call the linearization tax, when you absolutely have to. When is that? Well, when enforcing hard uniqueness constraints, like our username example earlier, when managing distributed locks so 2 workers don't accidentally corrupt a file, when dealing with financial ledgers where you literally cannot afford to double spend, and during leader election algorithms to prevent that nasty split brain. For almost everything else, eventual consistency is usually the better, much faster choice. Which leaves us with one final thought to ponder. Take a hard look at the systems you're building or maintaining today. What promises is your architecture making to your users right now? Are you projecting a single copy illusion that you can't actually back up when the network inevitably fails? Or are you paying a massive coordination tax for data that could easily tolerate a little bit of replication lag? Understanding these models is the key to building truly robust, data-intensive applications. Thanks so much for joining me on this explainer, and keep building great systems.